These are the notes for target C3.2b/4.3 D, F, and G. We're going to talk about how molecules interact and attract with one another. So one of the things we have to look at is what we call the VSEPR theory. Okay, the VSEPR theory states that because electron pairs repel, because electron pairs repel, molecular shapes will adjust. Okay, what does that mean? They're going to adjust so that the valence electrons, the ones on the outer shell, and the ones that they're sharing, so that those pairs are actually as far apart as possible. So let me show you what I mean. If we were to look at the structure CH4, okay, we've been doing dot structure. So if we start with that dot structure, we know that carbon has 4 valence electrons, and we know every hydrogen has 1 valence electron. So we can see where they're going to go. 1 will go on each carbon. And so when you draw the full dot structure for CH4, H will share there, another H will share here, another H will share here, and another H will share here. Now remember, this is our structural formula. It shows you how they bond together, but it doesn't show you the actual shape. Okay, so in the structure, all of these electron pairs right here are going to repel from one another. And drawing it this way shows that their angles are all 90 degrees from each other, all in one plane. Well, that's not going to happen. That's not as far apart as they can possibly get. So you have to picture a three-dimensional picture, and what's going to happen is you're going to have C in the middle. You'll have one H coming straight up. Okay, coming straight up. You'll have another one that is going slightly back, another one that's going slightly back, and then another one that's coming out in the front. Sometimes we'll just draw it like this so it looks like a little tripod on the bottom. Okay, this is known as a tetrahedral. This is the farthest apart that any atoms can get. A better way to, let's see if I can find a picture for you. A better way to look at it would be right here. This is a tetrahedral. Notice they're going to get as far apart as possible. Okay. Now, there are other variations, but this is your standard one because with this one you have 8 valence electrons around your central atom. And again, that's what our central atom is trying to do, is trying to get 8. Now, there are some variations on this. Okay. One variation comes with NH3. Okay. You draw the dot structure for NH3. N has 5 valence electrons. So you'll have 1 hydrogen here, 1 hydrogen here, 1 hydrogen here. And so when we go to draw this tetrahedral, you're going to have your 4 lines for your 4 pairs, your 8 valence electrons, and then you'll have a lone pair here. Now remember, this does take up space, and then you'll have your hydrogen, and hydrogen. And so then when we look at just the structure of the atoms, this is what we are seeing. We don't see that lone pair in the structure, and it gives it a different shape. Okay. And again, these lone pairs actually push down even more, making these angles smaller than in CH4. This is called a pyramidal. Now, you won't have to memorize all of the shapes. You just have to know that they all are based on the tetrahedral. So that's the one you'd have to look at. Another one would be water. If we draw water, water has 6 valence electrons. 1 hydrogen here, 1 hydrogen here. And so you do your water, and you've got your 4 pairs. You've got 2 lone pairs, and then your hydrogens. And then when you just draw your hydrogens without the lone pair, you get this, and we call this a bent shape. Those are your most common. Now, if you have something, I'm trying to think of, you could have what they call a linear triatomic. That would go straight in a line, but that would be something where, like BeCl, okay, which is an exception to the rule. It has just 2 electrons there. In order, if we wanted to get chlorine as far apart as possible, it's 180 degrees. That makes it linear, not bent. This one becomes bent because you have 2 lone pairs that are pushing down on your hydrogen. This is going to affect what we call polarity. So when we go to look at polarity, we'll understand why some atoms can attract to each other and some cannot because of their shape. All right. Now there are a lot of other shapes, but these are the most common ones that we will be seeing. Now that we have our shapes, again, if we want to know if a molecule is polar, if it has the ability to attract to itself or other molecules like it, one thing, again, you do have to look at is the shape, but you also have to look at the bond itself. Okay. We have what we call a non-polar covalent bond and a polar covalent bond. Okay. They're both covalent, so you're still talking primarily metals, or nonmetals and nonmetals bonding together and sharing of those electrons. So your water, your ammonia, your methane, those are all molecular compounds made up of nonmetals, and they're sharing their electrons. Beryllium, it will depend on what atom it bonds with, whether it will be ionic or covalent. So when you have a nonpolar covalent bond, that means you are sharing the electrons equally between the 2 atoms. Here on polar, you are sharing unequally, which means one atom will have the electrons more than the other. Now, how do you know if it's going to be sharing equally or if it's sharing unequally? Let me move this around just a little bit. Okay. So, what you're going to use will be electronegativity values. Okay. Electronegativity, remember, is the atom's ability to attract, a shared pair in a bond. This was one of the patterns that you had in your periodic table. The higher the number, the greater attraction it has. And so we don't memorize the values of these, but we have a chart that we can look them up on. Okay, for instance, if you had HCl and you look up the values for HCl, the electronegativity value for chlorine is 3.5. The highest number you can have is 4, so that's a pretty high number, which means it has a very strong attractive force, where hydrogen is a 2.1. So what that means is that the chlorine is going to have a greater attraction for those electrons. It's going to pull more. So in a tug of war, it's going to lean more towards the chlorine versus the hydrogen. And that causes what we call a dipole. Okay, so it's going to create a dipole. So your chlorine, since it has the larger number, this is the one that's going to be slightly negative. And so they use a little sigma and a little negative. And then since hydrogen is going to be lacking it because chlorine's pulling on them, this one becomes slightly positive. And then what you have is a dipole. One end is positive, one end is negative. Now again, it's not super strong like ionic, but it still gives you the ability to attract. Now, this is what we call a dipole bond, or a polar bond. If we were to look at CH4, again, hydrogen is a 2.1. Oh, and I can't even remember carbon. Carbon's slightly higher. It will pull that way, and it will have a dipole. That bond will be polar, but all the hydrogens are alike, and this molecule here, you can actually divide it up and see a positive and a negative. This molecule, you can't. These are all slightly positive, and your slightly negative is in the middle. So all around, it's positive. So you have polar bonds, but you have what we call a non-polar molecule, because we can't separate the charges. It's completely surrounded by positives. That's where shape comes in. This is symmetrical, so that they kind of cancel out. This one is not symmetrical, so we've got one each. So if we were to come back up here and we look at water, you look up those values, hydrogen is slightly positive, oxygen is slightly negative, and you have a polar molecule because of its bent shape. Same with this right here. You've got slightly positive, slightly positive, slightly positive. This one's slightly negative because of this lone pair up there. I have a negative on top and a negative on bottom, which again gives me a polar molecule. So shape plays a big part in the polarity of a molecule. Okay. So to get a polar molecule, you have to have both a polar bond and a shape that will allow you to separate those charges. Okay. So how do we know for sure whether or not it's going to give us a polar bond? Let me flip this over. All right. What you're going to do is you're going to look up electronegativity values, and then you're going to subtract them. Electronegativity difference. Okay, remember, difference means subtract. If you get a difference that is less than 0.4, it is non-polar. Okay. If you get a electronegativity that is greater than or equal to 0.4, but less than 2.0, you're going to have polar. If you have something that's greater than or equal to 2, you actually will have ionic. It means the difference is so great that it just completely removes the electrons, and you end up with a positive ion and a negative ion instead of something that's slightly positive or slightly negative. The electronegativity values can be found on page 405 in your book. And again, that's what we would use to determine if something had, if it was ionic, covalent, polar covalent. So let's take a look at some examples here. If I can, here we go. So let's say we have a bond between H and Br, and we have to identify what it is. You go to the table on page 405. Hydrogen is a 2.1. Bromine is a 2.8. So we know that the difference in this case is going to be a 0.7. Okay? When you memorize these numbers, you can see 0.7 is going to give you a polar bond. Okay? If we have like lithium and oxygen bonds, lithium is going to be a 1.0. Again, it's coming from this table on page 405. And oxygen is a 3.5. That gives us a difference of 2.5. Okay? That means we're going to have an ionic bond. Now, if you were to have one between hydrogen and hydrogen, you got 2.1, 2.1, your difference is 0. This would be non-polar. Non-polar bond. And then you'd have to look at the shape of the molecule to tell if the molecule was polar or not.